it is assumed that you are already familiar with the basic integration formula. The integral of u to the n du is equal to u to the n plus 1 over n plus 1 plus c if n is not equal to minus 1. If you aren't familiar with this formula and how to apply it, you should first watch the videotape entitled Introduction to Anti-Differentiation, which is also available in A220, before you watch this one. Okay, so now I can assume that everybody knows this formula and knows how to use it. In Chapter 8 of Leithold, you're introduced to the natural, logarithmic, and exponential functions. We will start with the differentiation formulas and work our way up to the integration formulas. If y is equal to the natural log of f of x, where f is a differentiable function of x, and f of x is greater than 0, then in Chapter 8 it is proven that the derivative of y with respect to x is equal to the derivative of f of x divided by f of x. Okay, we have the natural log of a function of x. We want to find its derivative with respect to x. It is simply the derivative of the function over the function. For example, if y is equal to the natural log of x to the 4th plus 2, derivative of y with respect to x would be, according to this formula, the derivative of x to the 4th plus 2 divided by x to the 4th plus 2. If y is a natural log of f of x, dy dx is derivative of f of x over f of x. So if y is a natural log of x to the 4th plus 2, derivative of y with respect to x is the derivative of x to the 4th plus 2 over x to the 4th plus 2. And then we can just fill in the derivative of x to the 4th plus 2 with respect to x is 4x cubed. The derivative of 2 is just 0 over x to the 4th plus 2. Let's do some more problems using this formula. If y is equal to the natural log of x cubed, the derivative of y with respect to x is equal to the derivative of x cubed with respect to x divided by x cubed. Or 3x squared, which is a derivative of x cubed, over x cubed, which is equal to 3 over x. By the way, another way to do this problem would be to make use of one of the properties of logarithms that are proved in Chapter 8, that is proved in Chapter 8, Section 1. This property tells us that the natural log of x cubed can also be written as 3 times the natural log of x. And if we have the natural log of x to a power, we can bring the power down in front and make it the power times the natural log of x. If we do that, then the derivative of y with respect to x would be, well, we consider this a product, so it would be 3 times the derivative of the natural log of x, which is 1 over x, plus the natural log of x times the derivative of 3, which would be 0, and of course we get the same answer, 3 over x, that we got over there. Now suppose y is equal to the natural log of x, all raised to the 3rd power. This is not the same as the problem that we just considered. Previously we considered the natural log of x cubed. These are different problems. Okay, here it's natural log of x all cubed. This was the natural log of x cubed. In this case, you could bring the 3 down, but not in this case. Okay, now we would like to find the derivative of y with respect to x. Just because you see a natural log of x, you don't start jumping in and using our new formula. First you have to analyze what type of a function we're dealing with. This function is set up similarly to something like this. Say y equals x squared plus 2 to the third power. And we wanted to find the derivative of y with respect to x. This is something you learned how to do last term. The derivative of y with respect to x, in this case, move it over a little, would be equal to the power, 3, times the function x squared plus 2 to the 1 less power times the derivative of x squared plus 2. Or 3 times x squared plus 2, quantity squared, times 2x. In other words, we had a function raised to a power. We used the chain rule to find the derivative of y with respect to x. We got the power times the function to the 1 less power times the derivative of the function. This is the kind of procedure to use over here. Now, y is a natural log of x to the third power. It's set up like this. It is a function to a power. We would like the derivative of y with respect to x. It will be the power, 3, times the function to the 1 less power times the derivative of the function. Exactly matches what we did over here. We did power, function, 1 less power, derivative of the function. The same thing over here. Power, function, 1 less power, derivative of the function. And we finish this up by saying we have 3 times the natural log of x to the second power. The derivative of the natural log of x is simply 1 over x. And that is our answer. So just because you see a natural log in the problem, that does not necessarily mean you're going to jump right in and start taking the derivative of the function over the function. You have to see exactly how the function is set up. Let's consider one more problem. Let's say y is equal to x cubed times the natural log of 2x plus 3. Make my x's look alike. Okay, once again we have the natural log of a function, but it appears as part of a larger setup. Right here we could think of this as a product. It's x cubed times the natural log of 2x plus 3. This should be differentiated by the chain rule, by the product rule. In other words, we will have the first function, x cubed, times the derivative of the natural log of 2x plus 3 plus the second function, the natural log of 2x plus 3 times the derivative of x cubed. As I said, this is a product. You have to differentiate this by the product rule, which you learned last term. This is first of all. On the way, we're going to need the formula that we have just had for the natural log of a function of x. But first and foremost, this is a product. It's going to be x cubed times the derivative of the natural log of 2x plus 3 plus the natural log of 2x plus 3 times the derivative of x cubed. Okay, so we'll get x cubed now. The derivative of the natural log of 2x plus 3 will be the derivative of 2x plus 3 with respect to x, or 2, divided by 2x plus 3. Right? The derivative of f of x over f of x. The derivative of 2x plus 3 over 2x plus 3. Plus the natural log of 2x plus 3 times the derivative of x cubed, which is 3x squared. Giving us a final answer of, let's see, where can I write it? Two x cubed over 2x plus 3 plus 3x squared times the natural log of 2x plus 3. The second differentiation formula that we'll need from Chapter 8 is the one for differentiating e to the f of x power, where f is a differentiable function of x. In Chapter 8, we find out that the derivative of y with respect to x in such a case is equal to e to the f of x times the derivative of f of x with respect to x. If we start off with e to a function of x, we want the derivative of y with respect to x. Derivative will be e to the f of x, rewrite it as is, then multiply by the derivative of the power with respect to x. For example, if y is equal to e to the x cubed, the derivative of y with respect to x would be equal to e to the x cubed times the derivative of x cubed with respect to x, or e to the x cubed times the derivative of x cubed with respect to x, which is 3x squared. Let's try another example with e in it. Let's say y is equal to e to the 2x divided by x squared, and we would like the derivative of y with respect to x. Well, the derivative of y with respect to x will be equal to. Now, just because we have the e to a power in it, it doesn't necessarily mean we're going to use our new formula immediately. What we have to do is realize that first and foremost, this is a quotient. So we must use the quotient rule to differentiate this. The derivative of a quotient is going to be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Let me finish it off over here. We then get that derivative of y with respect to x is equal to the denominator, which was x squared. Now the derivative of the numerator. Remember, the original problem is e to the 2x over x squared. This is what we're trying to differentiate. The denominator times the derivative of the numerator, but the derivative of the numerator, since the numerator is in the form e to the f of x, will be e to the power times the derivative of the power, e to the 2x times the derivative of 2x, which is 2 with respect to x, minus the numerator times the derivative of the denominator, which is 2x, all over the denominator squared, which was x to the 4th. We can simplify this a little. We see that both terms in the numerator have a 2x e to the 2x in them, so we can pull that out. 2x e to the 2x. We'd be left over here with an x to give us 2x squared e to the 2x. Take away here 1. because we just have 2x, e to the 2x, divided by x to the 4th. And you can divide numerator and denominator by x. So we would get 2e to the 2x times x minus 1 all over x cubed. Once again, what we had was a quotient. We found the derivative of y with respect to x by saying the denominator times the derivative of the numerator. And when we found the derivative of the numerator, we had to use the formula for e to the f of x power. Minus the numerator times the derivative of the denominator all over the denominator squared. And then we just did a little simplification. Now, by reversing the two differentiation formulas that I've just given you, we can develop two very important integration formulas. The first of these is the integral of du over u is equal to the natural log of the absolute value of u plus c. This comes from reversing the differentiation formula with a natural log of f of x. Now, as an example of this, consider the problem. The integral of 4x cubed dx over x to the 4th plus 5. This is exactly in this form. Let us make the substitution and see. If u is equal to x to the 4th plus 5, the denominator, well then, du dx, the derivative of u with respect to x, would be 4x cubed. Du, the differential of u, would be 4x cubed dx. And we see that this is exactly in the form, the indefinite integral of du over u. 4x cubed dx is precisely du. X to the 4th plus 5 is u. This problem is an example of the integral of du over u. Copy down the substitution because I want to erase that. Well, if we want to integrate du over u, the formula tells us we should get the natural log of the absolute value of u plus c, or the natural log of the absolute value of x to the 4th plus 5 plus c, because u is equal to x to the 4th plus 5 in this problem. In this particular problem, we really don't need the absolute value, since x to the 4th plus 5 could never be negative anyway. And the absolute value of a positive number is just the number itself. As a second example, consider this problem. The integral of x dx over 5 minus x squared. Okay, if we were to let u equal 5 minus x squared, then du dx would be equal to minus 2x. The derivative of 5 is 0. Du would be equal to minus 2x dx. And we don't quite have du over u. But it's not that bad because we're only off by a constant. We would like minus 2x dx on top. We only have x dx. Well, we can take care of that. We can multiply by minus 2 on the inside of the integral and multiply by minus 1/2 on the outside of the integral sign. Now, the net result is that we're multiplying by 1. Minus 1/2 times minus 2 is equal to 1. And certainly we can always multiply by 1 and not change the value of the original expression. But in multiplying by 1 in the special form, we have now put the integral into this shape. Minus 1/2 the integral of minus 2x dx, that's precisely du. 5 minus x squared, that's u. So we now have it in the form minus 1/2 the integral of du over u. But we know that the integral of du over u would be the natural log of the absolute value of u plus c. Once again, the constant can go outside or inside the parentheses, right? It would be correct this way, or to say that minus 1/2 times a constant is just some other constant, and leave out the parentheses. Anyway, minus 1/2 the integral of du over u would be minus 1/2 log of the absolute, natural log of the absolute value of u plus c, or minus 1/2 the natural log of, now what was u? It was 5 minus x squared. So natural log of the absolute value of 5 minus x squared plus c. This was our substitution. Now the second integration formula that we get in Chapter 8 comes from reversing the formula for the derivative of e to the f of x power. And what we get is that the integral of e to the u du is equal to e to the u plus a constant. This brings our total of integration formulas to 3. We have the u to the n du1, the integral of du over u, and now the integral of e to the u du. As an example of this formula, consider this problem. So we want to integrate x e to the 3x squared dx. This is almost in the form e to the u du. If we were to let u be equal to 3x squared, then du dx would be equal to 6x, and du would be equal to 6x dx. We almost have e to the u du. Right? If we rewrite it like this, we have e to the 3x squared times x dx. Now, we would love to have e to the 3x squared times 6x dx, because 6x dx is du. So what we're going to do is to multiply by 6 inside the integral. And of course, you can't do that unless you pay for it by dividing by 6 on the outside. So your net result is that you multiplied by 1. 1/6 times 6, that's 1. But we've now put this integral in the form 1/6 integral of e to the 3x squared, that's e to the u, 6x dx, that is du. And we know that to integrate e to the u du, we simply get e to the u plus a constant. So 1/6 e to the u plus a constant. And going back to the original variable x, by letting u equal 3x squared, we get a final answer of 1/6 e to the 3x squared plus c. Now, so far it's been pretty easy. I've been giving you a formula, and after I give you the formula, we do a few problems using that formula. It's a little harder when I give you problems and you don't know which formula to use. Let me first remind you of the 3 formulas that we have so far. Can I have the formulas over here on the board? Thank you. Okay, these are the 3 integration formulas that we've had so far. The integral of u to the n du is equal to u to the n plus 1 over n plus 1 plus c if n is not equal to minus 1. This formula was from earlier in Leithold, Chapter 5. The integral of du over u is the natural log of the absolute value of u plus c. This is the one we just worked out. And finally, the integral of e to the u du is e to the u plus a constant. Okay, now we're going to do integration problems, and one of these three formulas is going to be used in each one. Let's start with the integral of x cubed. Let me just move it a little over. X cubed dx over x to the fourth plus 7. Okay, now we have our three formulas. We'll need to use one of them. Since I see the fraction, I might think in terms of the du over u. After all, the derivative of x to the fourth plus 7 is 4x cubed, and I almost have that upstairs. So if I make the substitution, u is equal to x to the fourth plus 7, well then, du dx would be equal to 4x cubed, and du would be 4x cubed dx. So we almost have du over u. To get du over u, all I have to do is to multiply by 4 on the inside and divide by 4 on the outside. This problem would then be in the form 1/4 of the integral 4x cubed dx, that is precisely du, x to the fourth plus 7, that's u. And using the second formula on our chart, the integral of du over u is the natural log of the absolute value of u plus c. So we get 1/4 of the natural log of the absolute value of u plus c, or 1/4 of the natural log, the absolute value of x to the fourth plus 7 plus c. And once again, the absolute value is not really necessary in this problem.